Hello and welcome once again in this MOOC course on control system. In previous class, we have discussed the effect of feedback on stability and gain. In today's class, we will discuss the effect of feedback on sensitivity, that is the very useful term used to assess the performance of control system, especially in changing environment. So performance is assessed by using the term sensitivity, and we will discuss the sensitivity. Two cases we will discuss. Number one is sensitivity of overall transfer function with respect to forward part transfer function, that is GS, and with respect to GS in two cases we will discuss. Number one, in open loop case and in closed loop case. Closed loop control system. We have already discussed the effect of feedback, how feedback is useful to reduce the parameter variations, and we have analyzed the effect of feedback on stability and gain. So this sensitivity, effect of feedback on sensitivity, we will discuss in this class, taking two cases for open loop and closed loop system, and we will find the sensitivity of overall transfer function with respect to forward part transfer function, that is denoted as GS. And in second case, we will take sensitivity of overall transfer function with respect to for feedback part transfer function. In second case, we will take feedback path transfer function. Obviously, it is in closed loop only, transfer function, and this is only for closed loop control system. In open loop, we don't form the feedback path, so this will be applicable only for closed loop case. So we will take HS. So this is the topic of discussion for today's class. This sensitivity is a term which is mathematically represented in this way. Suppose we are taking output variable C, and there is change in output variable because of forward part transfer function G. Then this is represented in this manner: percentage change in output variable C. This is percentage change in forward part transfer function G. This is written as delta C upon C. This is delta G upon G. This is the mathematical representation of sensitivity. This is the sensitivity percentage change in one variable because of parameter variation. Because of parameter variation, suppose this variation is transfer function g, then it is written in this way. This is the ratio of change in output variable to the change in parameter variation, that is transfer function g. So this is delta c upon c, delta divided by delta g upon g. This is the sensitivity. This is the relation, mathematical representation of sensitivity. Mathematical representation of sensitivity. So we will find the sensitivity of overall transfer function with respect to forward part transfer function for these two cases, open loop and closed loop. And in second case, we will take feedback part transfer function to evaluate the sensitivity of overall transfer function with respect to feedback part transfer function. So this is the objective for today's class. So in first case, first one is open loop case. Open loop case. In open loop case, the overall transfer function that is represented by ms is ratio of output variable to input variable, that is rs, and this is called as transfer function gs. This is the case which can be represented by, which is represented by this block diagram. This is input is rs, this is transfer function gs, and in response to this input we have output divided by cs. ms is overall transfer function. ms is overall transfer function. Overall transfer function. So this ms, suppose this is the equation 1. From this equation 1, we can we can take this ratio of ms and gs. Obviously, this is equal to 1. This is equal to 1. And we have to find the sensitivity of overall transfer function m with respect to forward part transfer function g. This is m, this is m, this is m. So mathematically it is written in this way: delta m by m. This is delta g by g. So this is written in this way: delta m by delta g into g s upon ms. Actually, ms upon this is in Laplace transform. Actually, this is in Laplace transform form. So all are in S domain. All variables are in S domain. This is understood. All these quantities are in Laplace transform or in S domain. So this is this sensitivity. We have to find this relation. We have to determine this ratio and this ratio. So this says ms upon gs, which is 1. This is already given in here. From equation 1, we can find this ms upon gs is equal to 1. So this ratio is already given, and we have to find this partial differentiative delta ms and delta gs. So again, using this relation, differentiating differentiating with this equation. So this will give delta ms is equal to delta gs, or we can write down this as delta ms upon delta gs is equal to 1. So this is equal to unity, and this ratio is also equal to unity. From this equation 1, we have determined two ratios. One is for gs upon ms, sorry, ms upon gs. I'm sorry, this one is ms upon gs, this is ms upon gs. This ratio is basically ms upon gs. Delta ms upon ms, this is delta ms upon delta gs, and this is equal to unity. So we can substitute this ms upon, okay, once again this is some mistake, yes. So this is ms upon this one is ratio of gs upon ms, and this is, so the gs upon ms is equal to 1. Yes, from equation 1 we can write, this is possible to write down this in this way: gs upon ms is equal to 1. This is, so please invert this, so this is, yes, this one is gs upon ms, which is equal to 1. So in place of this, substitute 1, and delta ms upon delta gs is equal to also 1. So finally we will get this sensitivity of overall transfer function with respect to forward part transfer function g. This is 1 into 1 is equal to 1. So this is unity. This is unity in case of open loop case. This is unity in open loop case. In similar manner, we can proceed for closed loop case. So for closed loop case, for closed loop case, overall transfer function taking negative feedback, considering negative feedback, is gs upon 1 plus gshs. We have already derived this relation for closed loop control system, in which we are utilizing negative feedback. This is the relationship for that particular case. So in this case also we have to find this overall transfer function, sensitivity of overall transfer function m with respect to z, that is the ratio of delta m upon m, delta g upon g, that is the relationship for sensitivity. So this will give g upon m into g upon m, and this will give m delta ms upon delta z s. This is s, this is s. So this is the relationship for sensitivity. We have to find this ratio gs upon ms and delta ms upon gs in order to determine this sensitivity. So as ms is already given, suppose this is equation number 1. So from here, differentiating with respect to g, so this will give delta gs is equal to, using differentiation rule to determine the differentiation of a upon b, that is well known. First differentiation of 1 differentiation of a, suppose this is one function f1t, f1t and f2t, these are two given function, then we have to apply the differentiation rule, dy dt for this. So we are applying the same same concept here. So this will give a differentiation of gs is 1 with respect to gs, and this is multiplied by 1 plus gs hs minus differentiation of this denominator with respect to gs, that will give you hs into this is multiplied by gs, and this is square of this 1 plus gs hs whole square. This is finally, after some manipulation, this can be written as 1 upon 1 plus gs hs square. This is 1 upon 1 plus gs hs square. This is equation number 2. This is equation number 2. So gs upon ms we can find from this relation. From equation 1, we can directly determine the ratio gs upon ms is equal to this can be written from this relation. We can find gs upon ms is equal to gs hs. This is gs 1 plus gs hs. From this equation 1, we can find gs upon ms. So this is equation number 1. Suppose this is equation 2. This is equation 3. Substitute 3. Substitute this. Yes, equation from equation 1 we have ratio of gs upon ms, which is equal to this. So substitute this gs upon ms from here. So this will give 1 plus gs hs. This is multiplied by delta ms upon delta gs. This one is 1 plus gs hs whole square. Finally, this will give 1 upon 1 plus gs hs. So this is the sensitivity in closed loop case of overall transfer function m with respect to forward path transfer function z. So this is the relation for closed loop case. We have relation for closed loop case. Yes. So this is the sensitivity in closed loop case. Finally, if we compare it with the open loop case, in open loop case, relation is unity. We have, this is for closed loop case, and for open loop case, this is equal to unity. This parameter, this sensitivity in open loop case is equal to unity for open loop control system. So it is obvious we are using feedback, then effect of variations will be reduced. So sensitivity is reduced by this value, by this factor 1 plus gs hs in closed loop case as compared to open loop case. This sensitivity is higher, that is equal to unity. So it is benefit of using feedback in order to reduce the variations because of parameter variation caused due to environment, changes in environment. So it is possible to reduce the effect of variation using feedback. if we are considering overall sensitivity of overall transfer function with respect to forward part transfer function. So we can take another case. Sensitivity we can determine in similar manner. Overall transfer sensitivity of overall transfer function with respect to forward part transfer function. In similar fashion, we can define this sensitivity as delta m upon m, ratio of delta h upon h. This is h by m into delta m upon delta h. This is to be determined for closed loop case. This is for closed loop case. These variables are in for Laplace transformed or in S domain. So this can be written in this way. So overall transfer function is ms. This is equal to gs upon 1 plus gs hs. Instead of forward part transfer function, this time we will consider feedback part transfer function. So differentiating with respect to HS, that is feedback part transfer function. So this will give delta ms upon delta hs is equal to this is simple differentiation using the concept of differentiation of two functions f1t and f2t. This is the differentiation process. We are taking the differentiation of two functions f1t and f2t. F1t is in numerator and this one is in denominator. So simple rule is differentiation of first multiply second function f2t minus differentiation of second function multiply first function f1t, and this is square of second function f2t square. This will be this we have already applied in forward part transfer case, and this will be also applicable here. Only difference is that instead of gs we are taking hs. So this will give minus of gs square upon 1 plus gs hs whole square. So delta ms upon delta hs, we have this ms upon hs, yes, hs upon ms. So this in this equation, this relation 1, substitute the value of this hs. Ms is already given, gs upon 1 plus gs hs, in place of delta ms upon hs, take this one. This is minus gs square upon 1 plus gs hs square. So this will finally give answer minus gs hs upon 1 plus gs hs. So this is the sensitivity. This is the sensitivity in case of feedback part transfer function. If we are going to determine the overall sensitivity of overall transfer function with respect to feedback part transfer function, then we have the relation that is given by this. Final answer is this. minus sign is appearing here, minus sign is appearing here, it means as compared to feedback forward part transfer function, in case of feedback part transfer function, there is minus sign, which is indicating that sensitivity in this case is crucial matter. So specifications of feedback element should be more rigid in case of feedback part transfer function. In case of feedback part transfer function, specifications of elements of feedback element, specification of feedback element should be more rigid as compared to forward part transfer function. So this is more sensitive as this is the case which is more sensitive. Sensitivity is crucial in case of feedback part transfer function. If we are going to determine the overall sensitivity of overall transfer function with respect to feedback part transfer function, then sensitivity is more crucial case as compared to forward part transfer function. So in this case, the elements used in feedback should be more rigid. Specification of such element should be more rigid as compared to forward part transfer case. So this is the completion of effect of feedback. We have taken the stability gain, and in this class we have covered the effect of feedback on sensitivity. So once again I repeat this. We have to find the sensitivity of overall transfer function with respect to GS in open loop case and closed loop case, and we will determine sensitivity of overall transfer function with respect to feedback part transfer function. As far as sensitivity is concerned, this is very useful parameter, or this is the term which is used to assess the performance of control system, especially in changing environment. So this sensitivity is the ratio of percentage change in one variable to the percentage change in parameter. If we are taking the output as one variable, and in this output changes occurs because of this transfer function g, then this relation is written in this way. So this is delta c upon c, this is delta g upon g. C is output variable, and there is change in c because of variations in g, that is the transfer function. So we have to find this in case A and in case B. So we have so this is the open loop case where overall transfer function is given by this relation. So we have to find the sensitivity, which is GS upon MS multiplied with delta MS upon delta GS. From this we have GS upon MS is equal to 1. Differentiating this equation, delta GS upon delta is equal to delta MS is equal to 1. So this is 1 and this is also 1. So overall sensitivity is also unity in case of open loop control system. In closed loop control system, overall transfer function is given by this equation. We have to find the sensitivity of M with respect to G, which is mathematically given by this equation. Simply differentiating this overall transfer function. So we have relation 3. So substitute value of GS upon MS and delta MS upon GS in equation number 2. So this is to be substituted here. and from GS upon MS is determined by this 1 plus GSHS, substitute here. So finally we will get 1 upon 1 plus GSHS. If we compare open loop case, sensitivity is higher for open loop case. In closed loop case, this is divided by 1 plus GSHS. So, and this is the case when we are taking feedback part transfer function, minus sign is appearing here, which is indicating that the specifications of elements of feedback should be more rigid compared to forward part transfer function. So with this, I conclude today's lecture. In next class, we will consider modeling of control system. So thank you very much.